Flux is a quantitative measure of the amount of a field directed through a surface. In this class, we will focus on gravitational flux, electric flux, and magnetic flux. The infinitesimal area vectors in these equations always point perpendicular to the associated surface. The magnitudes of these vectors are equal to an infinitesimal bit of area of the surface. The shape for these bits of area, and thus the associated equation, vary depending upon the geometry of the surface and the geometry of the field. Two examples of infinitesimal area vectors are a rectangle and a thin circle. An infinitesimal rectangle will work as an infinitesimal bit of area for any surface and field. However, it is not always the mathematically simplest bit of area to use. For example, if the field has symmetry or is constant along one axis of the rectangle, then we can use an infinitesimal bit of area with only one differential. Similarly, if the field or surface has circular symmetry, we should use a thin ring or circle as the infinitesimal bit of area. Other systems might require using the surface area of a cylinder or the surface area of a sphere. Flux is maximum when the field and area vectors are parallel. There is no flux when these vectors are perpendicular, and the flux is negative when these vectors are antiparallel. For a single surface, the orientation of the area vector is somewhat arbitrary. The area vector must be perpendicular to the surface, but can point in either direction away from that surface. In these cases, we often calculate the magnitude of the flux only, since the positive and negative sign of the flux is similarly arbitrary. Let's calculate the magnitude of the magnetic flux through the shaded area from the magnetic field of the current in the wire. For simplicity, let's assume the wire is infinitely long. Since we are calculating the magnitude of the flux, we can ignore the vector nature of the magnetic field and the infinitesimal area. We have already determined an equation for the magnetic field of an infinitely long current-carrying wire. For the infinitesimal area, let's use a rectangle with sides equal to dz and d rho. Putting everything together gives us the following equation. The limits of integration are from 0 to L along the z-axis and from r to r plus h along the rho-axis. We can treat each integral separably and move several constant variables outside the integrations. These integrations are fairly straightforward and give the following result. As discussed before, however, since this field is constant along any line parallel to the wire, we could have used a different infinitesimal bit of area. Since the magnetic field is a function of rho, but not of z, the integral along dz can be solved by itself. This integral is equal to the length of the rectangle, denoted by the variable L. We can therefore write the equation for the magnetic flux through the surface using the following expression. We see from this equation that an alternative infinitesimal bit of area is a rectangle with length L and height d rho. We should always be on the lookout for how similar symmetries in the field or surface area can lead to a simpler or more calculation-friendly infinitesimal area.